Good morning. Hope things are going well. A little bit cold outside, but warm in here, so that is nice. Okay, so yesterday we talked about convergence and divergence tests. I guess divergence tests? I think divergence tests is the term. Either way, we talked about the integral test and then the comparison test. So if you remember, the integral test, it was the idea where if you have a series, which is a set of numbers that are all added together, you can kind of be like, well, that's kind of like Riemann sums. And you can kind of say that delta x is, this is not a formal definition, delta x is kind of like 1. And so you can kind of say that, well, this Riemann sum is kind of like an integral, and if this integral converges, then the series itself will converge, which is mostly true. One of the caveats that's important, sometimes important. That's the nice thing about caveats is the exceptions really aren't important until they're direly important. The function has to be continuously going down, monotonic going down. The function can either go flat or down, but it can't go up. Going up is no. So your function has to continuously going down, and it has to be positive. Or it could be continuously negative. Idea, always going towards 0. Or slightly pausing, then continuing its journey towards 0. And then, so the idea then is you can take your series, n equals whatever to infinity, probably. And then we write that as a integral. And if the integral gives you a number that's not infinite, or gives you a number at all, then it's probably going to be convergent. The comparison test is basically just logic. It tends to get kind of confusing, but the general idea is you have a mystery function that you want to know if it converges or diverges. I know I drew this as a curve, where really this is a summation, so it would look more like Riemann sums, like little boxes. But if you zoom out far enough, the boxes will look like a smooth line. And the idea is, if you have a known function less than this known, and this known function is infinite, then something that's bigger than this infinite known function will also have to be infinite. Seem reasonable? Okay. And on the converse side, if we have a known function that is limited, known and less than infinity, that's not good notation, that's okay. This is limited, then we know if something is smaller than something that's limited, not infinity, then that thing that's smaller will also be limited and not infinity. Also seems reasonable. And that's the idea behind the comparison test. So today, we are going to do the ratio test and the alternating series test. Hardest part is always finding the color. Ooh, cyan. Okay. So, just to keep me on track, I'll write ratio and alternating series. And then we'll talk about, radius of convergence. Radius of convergence. Wonder if that'd be a good Star Wars title. Radius of Convergence. Nah. Maybe one of the... Definitely not one of the movies. Not big and flashy enough. Okay. So the idea behind the ratio test is you take the limit as n approaches infinity of a to the n plus 1 over a to the n. And if this is less than 1, then it converges. If it equals 1, then we don't know. And if it's, I guess, inconclusive is the correct term. And if it's greater than 1, then it diverges. Where this is considered to be a of n. This value that we're finding that we're using for each step of the summation of the series, that's the an, a subscript n. So this is saying you take the next value, the current value, do the ratio, go to infinity, and if it gives you a number that's less than 1, then it works. Then it converges. So I am going to do the ratio test on this guy right here. Whoop. Whoop. I'm going to need a drink for this one. Crystal Light. There's something that feels wrong about drinking Crystal Light out of a coffee mug. But I don't mind. I will survive. Okay. So we're looking a to the n plus 1. So start by writing limit as n goes to infinity. I should change colors to differentiate. It's a good point. Thank you for reminding me. So we'll have n plus 1 over e to the n plus 1 over n over e to the n. So we're taking the ratio test. This is, we added 1, put it down there, added, well, nothing, added, put that down there. And so when we have a fraction divided by a fraction, you multiply by the reciprocal. So we have n plus 1 over e to the n plus 1 times e to the n over n, which equals, oh, I'm going to cancel this out a little bit, e to the n times e. So then we can cancel out our e to the n's, and we have n plus 1 over e times n. Go like this. Now I'm going to factor out an n. So I'll have n. I know I should be keeping the limit as n approaches infinity along with all of these. That's okay. That's nope, 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 nope. I'm pretty casual about a lot of this, and your thought process might be like, wow, shouldn't you be, technically correct the whole time? And there is a lot of value in being 100% technically formal, but especially for the AP test, where you have so little time to do so many problems, it's really easy to get bogged down in technicalities and miss some of the big picture. And I think you lose something when you focus too much on details. I know that really kind of sounds like I am trying to justify my laziness. And to a certain extent, you might be right. But I think there is value in developing a spider sense without focusing on the details of the technicalities. Though, to paraphrase Futurama, technically correct is the best kind of correct. So, there's value in both. In this case, I'm good with where I'm at. Okay. So I'll write it in here now. Limit as n approaches infinity of 1 over e, which is just 1 over e. E is like 2.7 or so. And so 1 over 2.7 is less than 1, therefore converges by ratio test. So let's review real quick what just happened. So we had a series. A series is a set of numbers that are all added together. This is specifically an infinite set because it goes from 1 to infinity. Though this one also could go from n equals 0 to infinity. Sometimes you have to be careful about n equals 0 because you get divided by 0 and then universe explodes. Not the case in this one. A series is specifically different than a sequence because a sequence is just a set of numbers. It doesn't add the numbers together. we decided to go for the ratio test on this one. Ratio test is really useful for things when you see like e to the n, because when we did the ratio test, we took the a(n plus 1) value over a(n), basically the next value over the current value. And when we did that, we were able to factor out we were able to change the e to the n plus 1 to e to the n times e. That's the same idea as if you had 3 to the third, which would be 3 times 3 times 3, which would be 9 times 3, which would be 3 squared times 3. Same concept all the way along. We just did the same thing with e, which then let us cancel out the e to the n. We are left with n's, and we're able to factor out one of the n's. And when we factored out one of the n's, we're then able to cancel it out. This is similar to like when we looked at limits when we were first studying about derivatives. Factor out one of the values, cancel it out, and then you see what you're left with. And that gave us a value which is less than 1. And by the ratio test, if you are less than 1 when you go to infinity, then it converges. If it equals 1, you don't know. And then if it's greater than 1, then it diverges. So as a quick mental thought, you could be like, okay, what if instead we had e to the n over n? We basically reverse the two. Well, you could go through the whole ratio test again, and trust me on this one, you would end up getting e over 1 instead of 1 over e, and it would diverge, which would make sense because when you think about it, you have an linear here, and then you have an exponential here. And exponentials, they can get big really fast, very fast. And so the idea here is it makes sense then that it would diverge. And you get the limit is 2.7 or so e, and so diverging makes sense. Okay, that is the idea behind the ratio test. Clean up my board real quick. Oh. And do I want to keep that part? I might keep that part right there. Up, clean, clean, clean. I feel like I'm destroying so much stuff, and it grates against my soul to delete so many things. I'm a digital hoarder, you could say. My hard drives are just filled with stuff I've had for decades. Decades might be excessive, but I'm like, well, they're electrons. You can always have more electrons. You can have a lot more electrons than you can have like shoe boxes, but there is a limit. Okay, now here's the alternating series test. So the alternating series test is actually kind of cool. So lock that one in place. So the idea here is we have two functions. We have one that's -1 to the n, and you might be thinking, wow, that's awfully contrived to have just that value in there. Well, sometimes it gets a little bit disguised. We'll get to that. And then you have another function. So if you have a function that goes to 0, such as 1 over n, the harmonic series, which we already saw, and the series alternates, then from there we can go to 0. It will converge. So what we're seeing here then is you have something. So 1 over n looks something like this. And we're adding up all the Riemann sums underneath. Little boxes. But what's really happening, since it's alternating, is we're having alternating boxes. And when you add all those up, it will converge to a value. Whoop. We're not concerned with what the actual value is. We're just concerned with converging, diverging. And so the 2 points you have to keep in mind is, one, the function has to go to 0, and the other one is that the series has to alternate. So this -1, you might see it sometimes in something along the lines of maybe -1/2 to the n, where you can then look at this as -1 to the n times 1/2 to the n. Or it could show up as cosine of n pi, where what you're going to get is a -1 fluctuating back and forth, where this cosine then goes positive and negative over and over again in a periodic fashion. So if we had to determine if this converged or not, we would say limit as n approaches infinity of 1 over n equals 0, which in itself does not mean that that it converges. But when you combine that with the fact that it alternates, then we have converges. Convergence? Converges. And that's the general idea behind the alternating series tests. So, clean up the board slightly. Boom. Write up the rules for alternating series. Goes to 0 and alternates, meaning that there's going to be some form of -1 to the n. Okay, now let's look at an example for radius of convergence. Okay, so here is another example. Lock this guy into place. Whoop. Green. So looking at this at first, you see, okay, there's a lot going on here. And so it looks like, okay, we have an alternating series, but does this go to 0? And why do we have an x in here? So the question would be, determine the radius of convergence of this series. Infinite series, because it goes to infinite. And so the first thing we want to do is, so it means that what value of x does this converge? For what value of x does this diverge? So the first thought would be, well, does this converge or diverge at all? And which kind of test are we really going to bank on here? So you see we have some powers here, so you're thinking maybe power series. See -1 to the n, so maybe alternating series. Either one will work. And specifically the power series we're going to try to use in this case will be the geometric series. So if you recall, if we have something along the lines of, oh, that is a terrible summation symbol. There we go. Summation n equals 0 to infinity of r to the n, that will equal 1 minus r to the n plus 1 all over 1 minus r. And one of the key parts that's going to trip you up every single time is it needs to start at 0. And this one over here starts at 1. So I'm going to start by rearranging this slightly. So we have summation of -1 to the n. And then I'm going to move the 3 over. We'll have x plus 2 over 3 to the n. And then I'll have n equals 1, and then n equals infinity. So what I'm going to do then is, to get this to start at 0, I'm going to add in n equals 0, and then I'm going to subtract off n equals 0. So there's two things you can pretty much always do in math. You can always add 0, and you can always multiply by 1. So if we add, what we're doing here is we're adding 0 because we're adding one number and then we're taking it away. I know this is terrible notation. You'll get over it. So if n equals 0, this will be -1 to the 0 times x plus 2 over 3 to the 0. this goes to 1, this goes to 1, and therefore n equals 0 is 1. And so what we can do is we can combine this into n equals 0, n equals infinity, negative 1 to the n, all over x plus 2 over 3 to the n minus n equals 0, which is 1. Okay? So now we can do our geometric series. So the geometric series, up here we had R. And one of the implications of R, cyan, is R is less than 1. Because if it was bigger than 1, then the geometric series would keep getting bigger and bigger. If it was 1, it would stay flat and then still be infinite. So we need it to be less than 1. So we get a curve. Our boxes are Riemann sums that look like this. And so this right here is our R. And so the radius of convergence then is, all right, we need this x plus 2 over 3 to be less than 1. It's okay for the series to alternate as well. So we could also say that this could be greater than negative 1. So we have, I guess this would be a diameter. And this would be a radius of how far x, the r value in the middle can be and still converge. That's my symbol for convergence. Convergence. So what we're going to do is we're going to take this inequality that we just had, so it'd be less than 1 or greater than negative 1, because we really don't care about the sign. We could use the alternating series test and be like, well, this has to go to 0. But I think it's more exciting if we use the geometric series. And that's just saying that we don't even care about the negative 1 to the n. That part could go away, and we are just going to use the geometric series portion. So, dark blue. Get a little drink. Delicious. Negative 1 less than x plus 2 over 3. Now one of the things you have to be careful about, I'll say maybe. You have to be careful about, I always start with you should start with a less than or equal to, because sometimes those are allowed, sometimes they're not. We'll check later. Another thing you have to keep aware of is if you divide by a negative number with inequalities, then you have to flip the sign. You kind of lose track of that with equals when you have an equal sign, because equals one way is equals the other way. So technically maybe you're flipping the equal sign when you divide by a negative number, but you don't notice because it's just equals. And that, to me, that's counterintuitive, but I do a lot of things through examples. Not to prove things, but to provide sufficient number of warm fuzzies. So you could be like negative 2 is less than 3, but you divide everything by negative 1, and you have 2 is greater than negative 3. I'm like, oh, yeah, that seems reasonable. Okay, let's do that. I'm going to take that one single example and extend it to everything. Now, that is probably unreasonable, but it is how I go through life. And you only need 60% of the test, 60% or so on the test. You can wing that. Be careful about winging it. Okay, so multiply both sides by 3. Negative 3 less than or equal to x plus 2 less than or equal to 3. Multiply 2, negative 5, or subtract 2 less than x less than or equal to 1. So x is between negative 5 and 1. And so what we're going to do is we're going to look at, I'm going to use this equation over here because it's easier on the eyes. negative 5, and 1. So if we plug in negative 5 here, we have negative 5 plus 2, which is negative 3, divided by negative 3, negative 1. Now, negative 1 would not be less than 1, so negative 5 will not work because we would get a graph. We'd get something that would be straight. I don't know if it'd be positive or negative. It'd probably alternate. Yeah, I don't know. So we'd have, it would stay at negative 1. So it would go straight. And that would provide an infinite amount of area underneath, so that would not work. But that would alternate with that, so it would probably be positive. Okay, so let's look at 1 then. So if we plug in 1, I'm just testing the endpoints to see if this should be less than or equal to or just less than. So we have 1 plus 2 over 3 to the n, which is 1 to the n. So then, but then we also have the alternating over here. So what would happen then is we would still have the boxes for the Riemann sums and the such. So this is the x, this is the y, that's a little arrow to show its axis, and I'll extend it down below. And so what we'd have, this is just a line, that's just a line. We get a box like this, box like that, and it would have this sort of sawtooth pattern back and forth. Not sawtooth, box form? I don't know. Little thing you see on top of castles. And so it would constantly alternate between, I don't know, what would be the first value here? 0? Would be 1. So I think it would alternate between, the summation would alternate between 0 and 1, just back and forth. But it'd do that forever, and so it wouldn't converge on a single value. And therefore, since it doesn't converge on a single value, it has two values that it alternates between, it does not converge, it diverges. So neither negative 5 nor 1 can be included. So it would be negative 5 less than x less than 1. And this is the radius of convergence. Depending on how it's phrased, the question might be looking for radius of 2. 2? Or is it 3? 3. Basically the distance, half of the distance between negative 5 and 1. Or it might be looking for the value, it might be looking for the answer, negative 5 is less than x less than 1. They're both the same type of problem, but it might be like, well, what's the possible values of x so that it converges? Which is a radius of convergence question, but they're not really asking for the radius of convergence, which would just be 3. So that is the idea behind, wow, that's a lot of writing. Sorry. That's the idea behind radius of convergence. And I try and stay away from a formal definition for radius of convergence because, to me, I would just see that question as, what is the values of x that allows it to converge? And like, oh, okay, then you just figure it out as opposed to trying to memorize another definition. And for this one, we could use alternating series, or as generally is preferred, if you see something that looks like a geometric series, go for a geometric series and use the formula n equals 0 to n equals infinity of r, where r has to be less than 1, is 1 minus r to the n plus 1 all over 1 minus r. And that's the idea behind a geometric series. Except I'm extremely right-handed and everything comes out crooked. There we go. Okay, I'm going to call that good. One more problem. So here we have a problem that would be similar to something you might find on an AP test. So, because I imagine you were wondering, well, what are we going to see on the AP test for something like this? Because a lot of these are pretty intensive, so you might see something in like a free response question, but for a multiple choice, it's difficult to ask good convergence questions. So, especially conceptual ones. This is a pretty good question. If the series, summation n equals 1 to infinity of a n, okay? Where an is just some portion sort of like this. Converges, okay, so they gave us that converges, and an is greater than 0. So they're saying does not alternate. For all n, which of the following must be true? We also know that n is greater than 0 because n goes from 1 to infinity. Okay, so the first possibility is, so this is the ratio test. They're talking about the ratio test. And they're saying, well, what must be true? So for something to converge, it has to be, if the ratio test is less than 1, then we know it converges. But if the ratio test equals 1, sometimes it will converge. So if this question was less than or equal to 1, then that would be true. But that's not what they asked. They said equals 0, which is not wrong. It's wrong. Nope. So if you get a limit as n approaches infinity for this, then you'd have to get less than or equal to 1 for it to possibly converge. And then one of the things they might be trying to confuse you for is limit as n approaches infinity of a to the n equals 0. So you're going to have to get some sort of function that goes like this, towards 0. And this last term, way over here at infinity, equals 0. So that goes down to 0. So the last term goes to 0. But the ratio of the last term and the second to last term may not be 0. Granted, I understand there's no actual second to last term when you're talking about infinity, but bear with me here. Okay, so that's what the first question is saying. Not true. So, A, no. The absolute value of n is less than 1 for all n. No, not true. Not necessarily true. So, let's say, just as a counterexample, 1 over n squared for n equals 0 to n equals infinity. N equals 1 because you divide by 0. Universe ends. This, for value, the first term here is going to be 1. And so you can have greater than terms that are greater than 1 and still converge. So no, all the terms for all n, not necessarily true. What they're probably trying to get you to think about here is the geometric series test. So, sorry, going back to the other example, I can multiply this by 9 and it would still converge. Because all I had to do was converge to a number. Not a small number, a big number, just a not infinity number. So then I could take this 9, move it into the inside, move it like that, and the first term would be 9. And then the second term would be 9/4. And then eventually it'd get down to, as you approach infinity, it would get to 0. But not all the terms have to be less than 1. The last term has to be less than 1. Specifically, the last term has to be 0. At least the limit as approaching the last term has to be 0. But the terms along the way totally can be whatever. Whatever that's not infinity. What they're probably trying to get you to think here is geometric series. So you have n equals 0 to infinity or 1. And so when you have an exponent like this, then r has to be less than 1. Absolute value of r has to be less than 1. So for a geometric series, an infinite geometric series, then you're going to need it to be less than 1. But this is not true. Not true. So that's the human performance trap that they are trying to ensnare you with. And this is why I think it's important to get kind of the concepts down so that you can see how these are logically don't follow. Man, and the sort of thing is, if you look at like a question like this, like when you're just starting out, it would create so many conceptual errors in your studying. Okay. Summation of all of them has to be 0. No, that's just not true. This is saying that the definition of convergence goes to 0. Not true. Convergence just means goes to a number, not infinity. So, nope, that's just not true. So, says the example, well, if we multiply it by n, then it has to diverge. That's not true either. I think we had an example earlier where we had something along the lines of n equals 1 to infinity of like n over e to the n. And we proved that converged. That converges because through the ratio test, because this one gets big pretty quick, but this one gets big crazy fast. And that the exponential getting faster, since you have it on the denominator, it's going to restrain the summation. And so you can multiply something by n and it can still converge. It just has to do with how, I guess, converging is a to the n. So not necessarily true. And this is saying, okay, so this could be done kind of like through the comparison test. So we know n is positive. It's specifically bigger than 1. So this says that we have some sort of thing, a of n, summation of a of n. This is the summation of a and n. I shouldn't write it like that, but I did. You understand. This is the function which holds a whole bunch of a and n's. And it says that if we take this, which we know is limited because it converges, and then we make it even smaller, it'll still converge. And so the idea is you have a set amount of something, and then you divide that to something smaller, you're still going to have something that's manageable, less than. So this would be done through the comparison test. And to be slightly more formal about it, you would say something along the lines of n equals 1 to infinity, a to the n over n is less than n equals 1 to infinity of a to the n. This converges. Therefore, the thing that is smaller than to it must also move over. There we go. Must also converge. So in this case, E would be the answer. Make sense? So this is actually a pretty good problem because it shows a lot of different thought processes and a lot of conceptual errors that are really easy to fall into. But if you have a conceptual understanding of what these divergence tests are doing, then you can sidestep them. All right, that is all that we have for this time. Next time we'll be moving on to Taylor series, maybe power series. They're kind of similar. The idea of your first, I probably should have said this in the beginning to like motivate you. I didn't. The whole reason that series are useful is because they are good approximations. Just like Riemann sums are good approximations for integrals. Power series, a type of series, similar to the geometric series, but not as restricted, are good for approximating functions. And so when you can't get a real answer, and you can kind of fake an answer through an approximation, and you can get really good at faking it, that's where specifically Taylor series and power series and series in general are useful. So thank you much, and I will see you next time.